a transverse contact vector field. B to sigma. Okay, so it means that there's exists at every, so it's a hypersurface in the contact manifold such that there exists a vector field which is transverse to the surface and contact, right? So it preserves the contact.
Does contact mean that it preserves the contact structure? Or
what's up?
Like the flow of V preserves the...
Yeah, it means it preserves the contact structure, yeah. Okay, so then hypersurface, yeah, so it's here basically so sigma, and then I have my vector field, which is like everywhere transverse, preserving xi. So a hypersurface, we say the hypersurface is conversely, or a hypersurface, let's say, is robustly non-convex. Maybe I'll add an adjective here, which is like CK robustly non-convex if it cannot be approximated by convex surfaces or convex hypersurfaces in the CK topology. So so basically it's saying like hypersurface is CK robustly non-convex if it has an open neighborhood that contains no convex hypersurfaces, right? Okay, so a question. A kind of long-standing question in contact topology, it's open for several decades, is do robustly non-convex, or maybe I'll say it like this. So I'll start by saying, are convex hypersurfaces dense in this kind of the space of embeddings of some surface of a hypersurface into your contact manifold. In other words, it may be in the CK topology. Alternatively, so just phrased in a different way, do robustly convex, so do CK robustly non-convex hypersurfaces exist. Okay. So the answer, this is a sort of important question for cut and paste operations in contact topology, which are sort of the reason you want convex hypersurfaces. I'm not really going to talk too much about the topological, like why convex hypersurfaces are important. They're very important for contact topology reasons, but maybe I won't go into that. But basically, this was an open problem for a long time. Of course, theorem is that in dimension 3, no. So also, in fact, convex hypersurfaces are C infinity dense. Okay. So this is a result of Giroux. Okay. And so a theorem, and then recently, basically a few years ago, or like a year and a half ago, I wrote a paper that proved that, in fact, there exists C2 robustly non-convex hypersurfaces in R2n plus 1. So if you, so this basically gave the first example of this kind of phenomenon of having something that cannot be convexly approximated. Another way to say this would be to say that convex hypersurfaces like fail to be dense in the C2 topology. They're not in general.
Yeah. Okay. Just so So it gets easier to be robustly non-convex as K increases.
It gets easier to be, yes. So like being C2 robustly non-convex is stronger than being C3,
Yeah.
which is, yeah, exactly.
Okay. So in the C2 theorem, definitely implies, say, the C1 or C0 theorem.
Yeah.
Or
I mean, if it's C0, the C0 theorem is actually false. So another theorem is that everything can be approximated by C0 in the C0 topology by a convex hypersurface.
Oh.
So really, this is a phenomenon that happens once you get to like C2.
Oh, okay. So I'm just getting confused with all the negatives. So
yeah.
If you have a C2 robustly non-convex hypersurface, it's definitely CK robustly non-convex.
Yes. Yeah. Exactly.
What is N?
Yeah, this robust. What's up?
What is N?
Oh, N is N is the dimension here. Yeah, here actually. Sorry. I should have said with N greater than or equal to 2. So yeah, sorry. So 3. So in 3, as I said, it's false. Yeah, so it's actually a specifically dimension 5 and higher thing.
So what about compact manifolds instead of R2n plus 1?
Oh, so any compact manifold has you can embed like a ball, like you can embed like an arbitrarily large open set inside of R2n plus 1. So in particular, if you have a compact contact manifold, then like it follows from this
You're
that
saying you can place these in a Darboux chart.
yes, you can place these in a Darboux chart. That is what I'm trying to say.
Okay.
So yes. Okay. So yes. So then
For C1, it's still unknown.
yes. Yeah. I can explain some conjectures about that later, but for C1 it's still open. Okay. So remark. Maybe just a remark about the proof. So this could use this. The construction was kind of created kind of specific examples using pools from partially hyperbolic dynamics. Okay, and maybe a couple of remarks. Specifically, use this tool called the blender, which will not show up too much in my discussion, but maybe a couple of remarks about this is that it's so it only works for kind of specific topology of the surface. Okay. So in particular, the actual hypersurface has to be of the form like S1 cross X, where maybe I'll say S1 cross SX, where this is like, or S star X, where S star X is like the coaster bundle of a hyperbolic manifold. Okay, so extremely restrictive class of hypersurface. Okay, it's only, as far as I understand it, it's very unclear to me if you should expect that the exact thing that I did there to work in more generality than that. And then the second thing is that it's actually a quite delicate construction. Much more complicated than I would like. Okay, so today what I'm going to explain is sort of an enhancement of this theorem. So this is work in preparation with my student, Michael Huang. So it'll come out. I'm definitely going to come out this year. It's really just a matter of me writing down a few more things. Okay, so the theorem is just that robustly, so C2 robustly non-convex hypersurfaces are actually like kind of abundant. In particular, they are C0 dense in the embedding in the space of this space of embedded hypersurfaces for any sigma and y. Okay, so for any choice of sigma and so in particular, no more constraints in the topology of sigma. One question that I actually posed in this paper was whether or not I said, in the kind of original draft of this paper, I said it would be extremely interesting if there was some kind of topological feature of the actual hypersurface that actually allowed you to do higher regularity approximation. And this basically the answer that this is giving you is that is not the case. It's not possible. And another way to think about this is sort of the strongest possible counterpoint to the sort of C0 density of convex hypersurfaces, which is given to you by Honda Huang. So this is just another paper on this kind of topic. Okay, so here, just as a little preview, so the proof uses basically an obstruction coming from well, maybe I'll say. So the proof uses an obstruction called a robust heterodimensional cycle. Okay. I will explain what that is later. But that's in fact most of the talk will just be me getting to telling you what this is and kind of explaining what it means. But yeah, so this is sort of the main thing. In fact, this kind of structure is extremely closely related to blenders, which is the tool that I used for the first paper. But it sort of gets more at the kind of mechanism of the obstruction a lot more. Okay, and actually the conjecture, which this is my conjecture, is that in fact there is a C2 dense open set U inside of this space of embeddings such that any maybe I'll say that such that for any hypersurface sigma inside of this open set, either sigma is convex or sigma has a so-called plus minus heterodimensional cycle, which is the obstruction that I'm going to explain later. So basically, my belief is that actually the thing that I'm going to explain to you, the obstruction to convexity that I'm going to explain to you in a bit, is like generically the full obstruction, meaning that kind of if you just perturb your surface, either you have this obstruction appears or you are convex. Okay, and I'll explain some reasons for that conjecture later. Okay, so let me now kind of explain some background about characteristic foliations to sort of explain this sort of obstruction or the proof of the theorem. Yeah.
Conjecture. When do you expect solving it to give like a different proof of the Honda-Huang theorem or something?
Maybe, yeah. We can talk about that after, but it's I'm not sure. I mean, I somehow like the origin of the motivation of this conjecture is related to that kind of thing. So some kind of simplification of Honda-Huang, but we can talk about it after.
So I guess well, if you assume the conjecture, then you would get your either convex or have a heterodimensional cycle. Then you can maybe just destroy the heterodimensional cycle.
Yeah, like that would be the idea. Is maybe what you could say is like first we create these heterodimensional cycles, and then we sort of try to simplify things by focusing just on the heterodimensional cycle. But in general, these heterodimensional cycles can be pretty crazy. So maybe I can maybe explain a little more later. Okay, so Okay, so first, let me kind of explain the background needed to understand this theorem or the conjecture and the tools. Okay, so first, any so any hypersurface in a contact manifold is equipped with sort of a natural dynamical system called the characteristic foliation. Okay, so the characteristic foliation so I'm going to think of this as like a singular kind of line field. So it'll be like a line field, except someplace like it'll be a family of lines, but some places it'll be zero. Okay. But you could also think of this equivalently as like a kind of singular one-dimensional foliation. So that's why I'm calling it the characteristic foliation. So it's also one-dimensional foliation with singularities. Okay. And and how do you define it? Well, I'm just going to define it to be the following thing. So it's the kernel of d alpha restricted to the intersection between the contact structure and the tangent space to the surface. Okay, as a vector space. And then you restrict this to and then this will be some subspace of this intersection between the contact structure and the surface. Okay, and this is for any contact form alpha on kind of the ambient contact manifold. Okay. So you take your contact structure, you restrict it to this subspace, right? So this subspace could either be all of the tangent space of sigma, or it could be the kind of, if the contact structure is transverse, then it will be some hyperplane inside of the tangent space of the surface. And then you take the kernel of this. Now, if T sigma is equal to the contact structure, then in that case, this thing will be like all of the tangent space, and this kernel will be zero. So those are like the singularities of it'll be everything, and those will be sort of the singularities. It'll be zero, and those will be like the singularities of the line field. Okay, and then in a place where they intersect transversely, this will be a one-dimensional subspace because this thing will be not a maximally non-degenerate two form on this thing. Okay, so maybe some pictures. So one example would be you have like the torus. If you just have like the foliation of the torus by circles, this is one example. You can get this example from like a pre-Lagrangian torus in a contact manifold. It's a bad drop of one of these circles.
So this is interesting because the contact distribution is non-integrable, right? Like if it were an integral plane field, then you could just make any surface transverse to it or something by a small perturbation.
Not necessarily.
Or I guess what I mean is if it were an integral plane field, you could just integrate the plane field to a disk or something. Transversality for manifolds, right?
Yeah, I mean, no, I mean, it would still, even if you were just looking at the intersection, yeah, okay, well, if this was, I mean, if alpha was integrable, then this would be not a well-defined line.
Yeah.
The fact that it's like a line field, that it's always a line field, it's sort of a property of the fact that alpha is contact. Anyway, so yeah, so there's some other, so another example would be kind of the foliation on this is like the unit 2. This is like just the 2-sphere instead of R3. I'm not doing a very good job here, but so there you actually have two singularities, the North Pole and the South Pole, and then a foliation by lines that go between the two singularities. Okay, and then another example actually is if you take like the cotangent bundle of S1. Then, so yeah, if you take like the cotangent bundle of S1, then this is like a hypersurface. This is not a closed hypersurface, of course, but it's a hypersurface inside of its own contactization. So an R cross T star S1. And then here, the characteristic foliation of that thing is basically the span of the Liouville vector field. So at each point away from the zero section, you get these lines, which are the integral curves of the Liouville vector field, and then along the zero section, you have a family of singularities along the zero section. Okay. So these are sort of three examples of characteristic foliations. So for me, a characteristic vector field Z is a vector field that spans the characteristic foliation. Okay. And then a characteristic flow is similarly like a flow who's generated by a vector field, which is characteristic. Okay, this is just terminology for later.
If you like fix a contact form, is there a
No.
natural choice of
No, so actually the thing that fixes one is if you fix a volume form. So if you fix a volume form and a contact structure, then then there's a canonical choice. So maybe I'll write it down for you. So if you fix so right here, so if mu is a volume form
on sigma or on the whole manifold?
on sigma.
Oh, okay.
Yeah. And alpha is a contact form. And let's say like lambda is like the restriction to sigma of a contact form. Okay. Then you can take Z satisfying this equation. And then this actually lambda. And then this equation actually defines the vector field. Yeah. Okay, so in fact, I think the better definition is somehow the better definition of this is actually that it's like the equivalence class of all such vector fields up to rescaling, because it's the definition of a singular line field is a little sketchy. Like, what does it mean for it to be smooth? You know, for example, it's just a little bit of a weird. Like, what is this actually? In what sense is this thing actually like a smooth line field, for example? And I think the best way to think about it is like it's like an equivalence class of vector field up to rescaling. Okay. Okay. So next, okay. So the following. So now, next, I want to introduce this kind of notion of a Liouville subset of a hypersurface. This is an extremely important definition for everything, but it's relatively non-standard actually. So it's not really it's a thing that's appeared in other places, but it's not something so familiar. Okay, so definition, a subset lambda inside of sigma is called Liouville if there is a choice of contact form alpha on Y such that if you look at the restriction of the contact form to sigma, this is a Liouville form on some neighborhood of lambda. Okay. So I will call this a Liouville subset. Okay. Now, okay. So let's think about this definition a little bit. So, actually, I want to introduce one more notion here. So, if sigma is oriented, we say that a Liouville subset is positive if there exists an alpha with alpha restricted to sigma inducing the given orientation, and it's negative otherwise. So if I orient, so if I orient the surface, then I can additionally ask for the Liouville form to either induce that orientation or to induce the opposite orientation. So then I'll say it's like negative Liouville or positive Liouville. Okay. Okay. So what are some examples? So an example is first any point P in sigma that is not a singularity of the characteristic foliation is both positive and negative. Okay. So if I have a point that's like a non-singular point of the characteristic foliation, then I can, in a neighborhood, I can choose a contact form where the contact form restricts to a Liouville form, and it can be both positive or negative. So it's sort of not near like kind of a generic point of the surface. It's sort of not a very meaningful thing. Like you can sort of be Liouville in both ways. Okay. So another example is any hyperbolic singularity is Liouville. Okay, so any hyperbolic, if I have a hyperbolic singularity, then it's Liouville. And moreover,
What's a hyperbolic singularity?
so a hyperbolic singularity means of the characteristic foliation. So it means like a hyperbolic plate, a point where the characteristic. So like I was saying before, so the characteristic foliation is you can think of it as like basically a vector field, right? And I mean like hyperbolic singularity means like a hyperbolic zero of that vector field. Okay.
Like a Morse critical.
Yeah, like a Morse critical point. Exactly, a Morse critical point of the vector field. Yes. Well, no, it could be a maximum remove. So hyperbolic by hyperbolic.
It's like a sink.
Yeah, so it could be a sink, it could be a source, just like a Morse type singularity, like a Morse type singularity of the vector field, but not like a rotation. Okay. So for a hyperbolic singularity, so yeah, any hyperbolic singularity is Liouville. Moreover, it's positive. Maybe I'll call it P. Okay. So moreover, if P is positive, then the index of P, which is like the Morse index of the singularity, has to be less than or equal to the dimension of sigma over 2. And if it's negative, then the index has to be greater than or equal to half the dimension. So actually, in this case, it's possible. It's in this case actually like in some cases you have to do one or the other. There's this sort of middle case where it depends on the specific critical point, but basically like if your index is very low, then you have to be positive. If your index is very high, then you have to be negative. Okay. Okay. Example 3 is any hyperbolic orbit. So now like a hyperbolic closed orbit of the characteristic foliation is Liouville. And there's a similar formula for the positive, or whether or not it's positive or negative via the index. So if you have a closed hyperbolic orbit, then there's actually a similar state. The first, it has to be Liouville, and then second of all, it has to be positive or negative depending on the actual sign. So this is this is an example of like so this is sort of an example where like you have sort of this mutual exclusivity of positive and negative. Okay. Maybe the last one, which I won't even write as an example, is like if you have the full surface, right? Then the full surface cannot be positive. If you have a full surface and it's closed, then it cannot be, the whole thing can't be Liouville, right? Because otherwise you'd have like this Liouville form on a closed manifold, which is not possible, right? Okay, so it's sort of, this is sort of some kind of non-trivial constraint on the set. And really, you should think of it as like somehow near this thing, it being Liouville means you sort of are like the germ of a Liouville flow, like the germ of the flow of a Liouville vector field. That's what the characteristic foliation looks like. Okay, so here's a theorem. Kind of crucial. Okay, so let's say that let lambda be a transitive, or sorry, let it be not yet. So let lambda be a compact invariant set of the characteristic foliation. Okay, so let's say I have like a compact invariant set. Then lambda. And let's suppose that that lambda is Liouville. Okay. Then lambda is either, and well, maybe I'll say lambda cannot be both positive and negative. Okay, so actually, if you're a compact invariant set, then actually you have to choose to be one or the other, and you're Liouville. So it's possible. Of course, the whole manifold is a compact. You know, if it's a closed thing, then the whole manifold will be compact. Will be a compact invariant set, and so clearly in that case, you're not either. Okay, but if you are Liouville, then you have to be one or the other. If you're compact invariant set. Okay, and actually the proof of this, which I probably won't have time to explain, is basically uses some kind of ergodic characterization of what it means to be Liouville. So basically, like if you're familiar with the McDuff criterion for Raveness, for being a Rave vector field, it's very similar to that. So like I have, and I can explain it to you guys afterwards if you want. But so this kind of the proof uses an ergodic characterization of being Liouville. So basically, it says that you're Liouville if there's some property. There's some property of your invariant measures that if it's satisfied, then you're Liouville. Okay. Okay. So now theorem 2. Okay. Is that and it's actually an application of the same tools for this first theorem are that any transitive hyperbolic invariant set lambda is Liouville. Moreover, okay, lambda is positive if the index of lambda is greater than the dimension of sigma over 2, or less than or equal to. And then lambda is negative if the index is greater than the dimension of sigma over 2. So this is a generalization of the statement for the hyperbolic orbits. Okay.
What does index mean here?
So the index is like if you have a hyperbolic invariant set, then you have the splitting if you have a hyperbolic invariant set, then you have a splitting of the tangent bundle into like a expanding direction and contracting direction. And this is the dimension of the negative. The index is like the dimension of the contracting direction.
Oh,
yeah. Okay.
So does this theorem work for like if you replace hyperbolic with just like isolated invariant set?
No.
That sounds a common. Or
No, I don't think so. Probably not.
Okay, so you're using the hyperbolic.
Yeah. So actually, I can kind of explain the proof. So basically, like there's some. So as I said before, here's like a sketch of the proof, right? So as I said before, there's some ergodic characterization. Basically, like there's some element of in the dual of the space of sign measures, such that if every measure with support on the invariant set is positive against that element, then it is positive Liouville. And if it's negative against that element, then it's negative Liouville, right? And so that's like sort of the theorem that goes, that's the thing that goes into this first theorem. And then for the second theorem, you just use the same, you just use this, and then you say, well, for a hyperbolic invariant set, the set of hyperbolic orbits as measures are sort of dense in the set of all invariant measures by the ergodic, by like Monet's closing lemma. And so then you just kind of apply that density to get the same, to get that the criterion holds for all measures on this thing. Yeah, so it's somehow using this, you can basically use like Monet's ergodic theorem as a kind of method of proof there.
I see. Yeah,
Yeah.
so you really can't prove hyperbolic.
Maybe there's something weaker you could say, but this is like the proof that I have, the simplest proof uses some kind of closing lemma that's true for hyperbolic invariant sets that doesn't maybe hold in general.
I mean, it seems like the best bet would be if you just assumed it was an isolated invariant set with like a shadowing property.
Yeah, something like that. But then the shadowing property, like most of the time, means you're hyperbolic or something. So,
Yeah, that's
Yeah.
Yeah, so it's like
Yeah. Okay. Okay. So anyway, so hyperbolic invariant. So basically, like if you're trying to understand like this Liouville-ness, these hyperbolic invariant sets are another case where you know that you are Liouville and you have to be like one or the other. Okay. Okay. So now. Okay, so now let me explain a convexity obstruction. Okay, and this is the convexity obstruction that sort of plays a role in all the theory over here. Okay, so so theorem. Okay, so let sigma be a convex hypersurface. And okay, and let lambda plus minus inside of sigma be compact invariant sets with such that lambda plus is positive and positive Liouville, and lambda minus is negative Liouville. Okay. Then in this case, there cannot be a heteroclinic. And I'm going to put a little asterisk here because I probably need to tell you what I mean by heteroclinic. It's like a little bit not immediate. There can't be a heteroclinic from lambda minus to lambda plus. And I'll write like an H there. Okay. So you can't have, so like, you know, I've got my like plus guy over here, or I got my minus, maybe my minus guy over here. Okay. And I have my plus guy over here. Okay. And I can't have, so, you know, morally speaking, a heteroclinic is like some trajectory, you know, H of the characteristic foliation that sort of limits to, on one side, it limits to your invariant set over here, and in the other direction, it kind of limits the invariant set over here. Okay, and really, actually, there's something a little weaker than heteroclinic that I could put in this theorem, which I don't want to explain because it's sort of complicated. And you know, when you have like, for example, like when lambda plus and lambda minus are like hyperbolic orbits or something, then this is literally, you know, an orbit in the intersection between the stable and unstable manifold. So it's like the usual thing you'd think about heteroclinic. But maybe I won't elaborate more on what heteroclinic means. Okay. Okay. So proof. Okay. So let me draw you a picture. So okay. So here's the proof. Okay, so if I have if sigma is convex, so sigma is convex, then basically extremely well-known topological property of convex hypersurfaces is that any convex hypersurface divides into a sort of positive Liouville domain sigma plus, and a negative Liouville domain. Sigma minus along a contact dividing set gamma. Okay, so if I have sigma here, then there I can split it along some contact submanifold. We'll call it gamma. Okay, so it's a contact submanifold of the whole thing. And then like a plus side and like a minus side. Okay, such that the plus side is positive Liouville and the minus side is negative Liouville. And the characteristic foliation points into sigma minus along gamma. Okay, so if you look at the characteristic foliation is sort of oriented, and if you look at it along gamma, you'll have this. It'll be pointing like that way, right? It'll be pointing from one side into the other. Okay, and now if I had so now because of this theorem about the well-definedness of being positive or negative for invariant sets, this guy has to be on the positive side, and then this other guy has to be on the negative side, right? So lambda plus has to be over here, lambda minus has to be over here. So as I was saying, it's possible if you did not know this about invariant sets, then it would not be you would not be able to say this, right? Like it would be there are sets where even though it's positive Liouville, it's also negative Liouville, so it could be on this side too, right? But for invariant sets, it has to pick a side, okay? And then if you had and then of course this precludes the existence of a heteroclinic going like this, because any such heteroclinic has to pass this wall that separates the plus and the minus side, right? So no can exist, right? So it's very simple thing. Okay, so basically, so somehow like the existence of this kind of positive Liouville and negative Liouville invariant sets are actually like, in some sense, this is like the universal obstruction. In fact, I could give you a theorem that actually like a complete characterization of convex hypersurfaces that actually characterizes convexity in terms of the non-existence of such invariant sets. It is like too long to explain this theorem, but I'm also again happy to say this later. Unfortunately, it's a hard to use theorem because it uses sort of Conley theory and like a weaker kind of invariant sets than hyperbolic ones. Hyperbolic ones are sort of the most useful. But anyway, so this is really a fundamental obstruction. Okay, so now what I would like, so then for this theorem up here, what I would like to do is say that, so what I would like to now do for this theorem is sort of construct robust examples. Like, if I want to construct a robustly non-convex thing, I want to construct robust examples of this heteroclinic that goes the wrong way, right? So I want to construct robust examples of this, something going from a negative guy to a positive guy. Now, if you go over here to this theorem about the hyperbolic orbits, it turns out that bad heteroclinics like this between closed orbits are actually in general fragile, meaning that if you just do an index calculation for the intersection between the stable and unstable manifolds, you'll see that actually generically, if you perturb it to be like Kupka-Smale, then there won't be any heteroclinics that are bad. Okay, so that means you really need something more sophisticated than hyperbolic orbits to make this happen. Okay, so now we kind of get to this main thing, which is these robust heterodimensional dynamics. Okay. All right, and now actually the story that I'm going to tell you is completely in the realm of topological dynamics. So for a few minutes, I'm just going to tell you things about from smooth dynamics. Okay, so here, let's say that maybe we'll fix a smooth vector field V on a smooth manifold M. Okay. So a robust heterodimensional cycle C of V is a pair of hyperbolic invariant sets with maybe lambda plus and lambda minus with heteroclinics. Oh, maybe I'll just say heteroclinic cycle for now, or heterodimensional cycle with heteroclinics from lambda plus to lambda minus, and then also from lambda minus to lambda plus. Okay, so this is very obvious definition. I don't know why they call it heterodimensional. I think the heterodimensional comes from the something I'll say in a little bit, but I would call it a heteroclinic cycle. Somehow heterodimensional cycle is the chosen dynamics terminology. Whatever. Okay, so it's a cycle of heteroclinics relating to hyperbolic invariant sets. Okay. So we say that that C is robust if it persists under C1 integrations. Okay, there's something more precise I could say about that, but basically it's you say it's robust if you C1 perturb your vector field, and for a small enough C1 perturbation, the cycle survives, right? Or some version of the cycle survives. Like there's a continuation of the cycle that sort of exists after the perturbation. Okay. Okay, so it's a little bit of a history lesson. So basically, the existence of these heterodimensional cycles was actually discovered by Abraham and Smale. So back in the 60s, Smale had this thing called Smale's dream, which was this concept that maybe structurally stable or axiom A vector fields or diffeomorphisms are actually dense in the space of all diffeomorphisms, right? Like this was what he wanted to be true because it would imply that structurally stable dynamics is like sort of generic, okay? And and then basically like Smale thought about this and thought about this and thought about this, and eventually he found these examples that proved that proved that his conjecture, his dream was wrong, okay? And those examples exactly occurred because of this kind of robust heterodimensional dynamics. So essentially these robust heterodimensional dynamics are precisely the mechanism that prevents hyperbolicity from being generic, okay? As far as dynamicists are aware. It's still actually a conjecture. That exact statement is still actually a conjecture, but this is like sort of the believed picture.
So if you're in like a Kupka-Smale setting where you have like two hyperbolic orbits and the stables and unstables intersect transversely, then
there will be no heteroclinic cycles between the orbits. This thing actually must, to be robust, it must involve invariant sets of larger size.
This is just some kind of dimension count.
It's some dimension count. Like literally, if there's a heteroclinic going one way and everything's transverse, then the heteroclinic in the other way will have to not exist because the stable and unstable manifolds will be basically the heteroclinic going one way will be dimension D, and the heteroclinic going the other way will be dimension negative. Like the space of heteroclinics going the other way will be dimension negative D.
Oh, okay.
If you or negatives, good. Something like that. So okay. All right. So okay. So really, this kind of mechanism of the robust heterodimensional dynamics is sort of very well known thing. And also another thing maybe I'll say about this is that robust heterodimensional dynamics are they are now understood using the language of blenders as well. So blenders, I'm not going to explain what a blender is, but blenders are what appeared in my first paper. They're something invented by like Bonatti and Diaz, and they solve many problems in sort of non-hyperbolic dynamics. But nowadays, I think these heterodimensional cycles really, the robustness of them is understood in terms of blender, the emergence of a blender inside of the dynamics somewhere. Okay. Okay. So now, so to plug a little bit of contact geometry into it. And I'm gonna wrap up soon because I guess I'm out of time. But okay, so definition, we'll say a heterodimensional cycle is so let's say C of the characteristic foliation. So now we're back to the setting of the hypersurfaces. So we'll say this is positive, negative if if one of the things is positive Liouville. So one of the hyperbolic invariant sets is positive Liouville, and the other is negative Liouville. Okay. So then theorem is that any okay, so any like sigma can well, yeah, let me say any hypersurface sigma inside of Y psi can be perturbed, the C0 perturbed, to have a possibly fragile positive negative heterodimensional cycle. Okay, and then moreover, and I'm writing a little short version of this because I'm running out of time. This cycle can be C infinity perturbed to a robust one. Okay, and then this theorem implies the density theorem that I said earlier, because basically what this says is that you can take a given hypersurface, you can perturb its characteristic foliation to produce one of these cycles by C0 perturbation, so that has to be kind of a big perturbation. Then once you have that cycle, you can then C infinity perturb the cycle to make it robust. Okay? Okay, so now let me explain this kind of the proof. Let me like kind of in the last like 2 minutes just kind of say a little bit about this proof. So how does the proof go? So basically the C0 perturbation to have a cycle is actually kind of easy. So essentially this is just like you literally look at a kind of a standard kind of flow box. So if you look at a point in your hypersurface, then you can sort of model it on the symplectization of a contact disk. So as kind of a hypersurface and in its symplectization or contactization. That's some kind of standard example. Then you can basically just work in coordinates with that standard example to produce a cycle. It's like not very hard. The deep part is actually the statement that you can do the C infinity perturbation to make it robust. And actually this C infinity perturbation part is actually an application of some very deep new results on these robust heterodimensional cycles by Lee and Turayev. So this is work that was actually done pretty much at the same time as the first paper that I talked about, the one from 2024. What they show is that you can construct these families of vector fields called unfoldings, which essentially have kind of families of these heterodimensional cycles. And if you do this in a sufficiently generic way, then for a generic parameter in the family of vector fields, the heterodimensional cycle in that family will be robust. So it involves a very complicated analysis of the different cases. But basically, the second part of the theorem basically amounts to just constructing a contact version of their unfolding construction. So basically, like constructing exactly this type of family that they call an unfolding, showing that it has the required properties, et cetera, et cetera. And so then you can essentially apply this kind of existence, this like very general existence theorem for these heterodimensional cycles. coming from the smooth dynamic side. Yes. Okay. Yeah. So maybe I'll say one more thing since it's not quite two yet. So the last thing I'll say about all of this is that maybe I'll go back to this conjecture.
We started kind of 5 minutes late, so you.
Well, okay, but I mean, I'll stop and then you guys can ask questions if you want. I want to say maybe a little bit about this conjecture. So why would I believe this? Okay. Well, so actually, I think it is reasonable to think about this as the analog of this conjecture that I was saying earlier about the dichotomy between heterodimensional dynamics and hyperbolicity, right? So there's a conjecture in dynamical systems, long-standing conjecture. It's named after somebody, but I don't remember who it's named after. That says that a C1 generic flow on a manifold is either axiom A, or it has a heterodimensional cycle, right? And this convex thing is sort of the analog of axiom A. So in fact, I can prove using a lot of the tools that I talked about here that an axiom A, something that's axiom A and satisfies strong transversality is convex. So this is sort of the convex side is sort of the axiom A part of that conjecture, and then this other thing is like the heterodimensional cycle part of that conjecture. So essentially, this is somehow some kind of contact version of the conjecture from smooth dynamics. So maybe that's the kind of motivation for the conjecture.
So by your result, if that conjecture was true, then this one would be true. Or
if which conjecture? If that conjecture were true, no, because you can't necessarily prove that. That conjecture is saying you can like do some constructions in smooth dynamics, but those you would have to like kind of repeat whatever proof they did in the setting of characteristic foliations to reprove it. So yeah. Okay. Anyway, so I'll stop there and we can talk more.
Yeah. Questions?
You guys asked a lot of questions during the talk, so maybe not many.
All right. So what's like or I guess you said that you gave an example where, you said, the heterodimensional cycles with periodic orbits are not robust because of this dimension count. Is there a similar heuristic definition for what a robust heterodimensional cycle looks like? It's like something where those stables and unstables have very high dimension.
Yeah, I mean, it's something where like the intersection, I mean, the blender picture would be that it's something where the intersection, if you look at the closure of the stable manifold of one of the things, then it has to be like much bigger dimension than you would expect. So like if you take an unstable manifold of like so the thing that these blenders do is they sort of have this property that like if you look at the intersection between the stable and the unstable manifolds, and then you look at the closure of that in one of the stable manifolds, then it's like a lot of stuff. And that property ends up being demonstrably like robust. So then that gives you like sort of it means that these like the intersection between the unstable and stable manifold, like if you do the naive calculation, it actually doesn't really match what's happening on the ground. Like what's happening, like if you actually look at the set that you're getting and then take some kind of and then take a closure, then like the set is sort of bigger. This is sort of it's a little bit of a complicated heuristic. It's not so simple as this. It's not so simple as this sort of picture for the orbits. Yeah.
So. So it's like the unstable manifold is if you look at it in like a flow box or something, is it like the unstable manifold?
I can draw you a picture
Yeah.
afterwards. Yeah. Any other questions?
So I'm a bit confused about so we said that it's robust under C1 perturbation.
Yeah. Okay, so the C1 topology on the characteristic foliation is like the C2 topology on the surface, because it's like the same way that like Hamilton, if you look at the CK topology on Hamiltonians, then that's like you lose a derivative when you pass to the vector field. So that's why this is C1 versus C2. Yeah, the C1 case would have to involve some kind of mechanism that's like complete. If the C1 case were false, then it would have to involve some kind of mechanism that's kind of strictly symplectic, actually, because yeah, I mean somehow the C0 dynamics picture is much more flexible. So yeah. Okay. All right, so we're good.
Yeah.
Cool.